Good morning, students. Last time we completed problems on first law of thermodynamics. Today we want to start another point of thermodynamics, that is enthalpy. Enthalpy, denoted by letter capital H. You know that in chemical reaction either heat is evolved or heat is absorbed. For example, we write general reaction A plus B react to give C plus D. So, in this chemical reaction, A and B are called reactants, C and D are called products. So, in this reaction, heat is evolved. Heat is evolved. Suppose in this reaction heat is evolved, then this reaction is called exothermic reaction. Exothermic reaction. And another reaction A plus B react to give C plus D. In this reaction heat is absorbed. Heat is absorbed. Then this reaction is called endothermic reaction. Endothermic reaction. So you know that heat is denoted by Q. But in thermodynamics, in chemical reaction, for heat, a special symbol is used that is called enthalpy, and it is denoted by letter capital H. So, for this reaction, change in enthalpy delta H is equal to negative because heat is evolved. And in this reaction, change in enthalpy delta H is positive. So, in thermodynamics, a special symbol for heat is used that is called enthalpy, denoted by letter capital H. Now, what is the scientific definition of enthalpy and its equation? Here, enthalpy H is equal to U plus PV. So we can define enthalpy as like this. It is the H, enthalpy is the sum of internal energy and energy equivalent to pressure volume work. What is called enthalpy? Enthalpy is nothing but it is the sum of internal energy and energy equivalent to pressure volume work, and mathematically H is equal to U plus PV. H is equal to U plus PV. Now, change in enthalpy, all this is equation number 1. Change in enthalpy delta H is equal to H2 minus H1. All this as equation number 2. So, change in enthalpy is given by the equation delta H is equal to H2 minus H1. H1 stands for enthalpy in the initial state of the system. H2 is called enthalpy in the final state of the system. So, delta H is equal to H2 minus H1. Here, from equation 1, we write H1 is equal to U1 plus P1 V1 and H2 is equal to U2 plus P2 V2. From this equation number 1, we can write for initial state, enthalpy in the initial state H1 is equal to U1 plus P1 V1 and enthalpy in the final state H2 is equal to U2 plus P2 V2. Then delta equal to U2 minus U1 plus P2 V2 minus P1 V1. P1 V1. That is equal to U2 minus U1. Sorry. Okay, delta H is equal to, delta H is equal to U2 minus U1, that is delta U plus P2 V2 minus P1 V1 means delta, in bracket we can write P2 V2 minus P1 V1, P2 V2 minus P1 V1. And you know that P2 minus P1 means delta P, V2 minus P1 means delta V. Then we can write delta U plus delta into PV, delta into PV. So we can write this equation as like this, that is, or at constant pressure, you know that P1 is equal to P2 is equal to P, P1 is equal to P2 is equal to P. That's why we can write this equation as like this, delta H is equal to delta U plus delta PV. Now, here, this is called as delta H is equal to delta U plus P delta V. This equation is the equation for change in enthalpy. Delta H is equal to delta U plus P delta V. Now, if from the equation, that is QP is equal to delta U, QP is equal to delta U plus P external into delta V. Now, if pressure of the gas and external pressure is same, then P external is equal to P. Then we can write QP is equal to delta U plus P delta V. So, from these two equations, we can write delta H is equal to QP. Delta H is equal to QP. And this equation indicates that change in enthalpy is equal to amount of heat evolved or absorbed. Okay, now next point, relation between delta H and delta U for a chemical reaction. Relation between delta H, relation between delta H and delta U for a chemical reaction, Now we want to know what is the relation between delta H, that means change in enthalpy, and delta U, that is change in internal energy for a chemical reaction. You know that at constant pressure and constant temperature, delta H is equal to delta U plus P delta V. So here delta V is nothing but change in volume, and those chemical reactions in which reactants are in solid or in liquid state, change in volume is very, very small, or it is negligible. Why? Because you know that solid and liquids are non-compressible. So here this equation becomes, that is here the value of delta V is nearly 0, it is very small. That's why this equation becomes delta H is equal to delta U. So, relation between delta H and delta U for a chemical reaction in which reactants are involved in solid or liquid state is given by the equation delta H is equal to delta U plus P delta V. Here, as solid or liquids are non-compressible, change in volume is negligible. So, P into delta V, that is, becomes, that means this equation becomes delta H is equal to delta U. So, in those chemical reactions involving solid or liquid, change in enthalpy is equal to change in internal energy. But in case of gaseous reactions, or those chemical reactions in which reactants and products are in gaseous state, then change in volume delta V is not equal to 0. Then we can write the equation, that is delta H is equal to delta U plus P delta V. Delta H is equal to delta U plus P delta V. In this reaction, change in volume is not equal to 0 because gases are highly compressible. Then change in volume cannot be neglected. So this equation becomes delta H is equal to delta U plus P into delta V, that means P into V2 minus V1. So delta H is equal to delta U plus PV2 minus PV1. So here the reactions involving gaseous reactants and products, this equation becomes delta H is equal to delta U plus PV2 minus PV1. Now this equation is called as equation number 1. This equation is called here equation number 1. Now here, suppose these gaseous reactant and products behave ideally. Suppose these gaseous reactant and products behave ideally, then from ideal gas equation PV is equal to nRT. PV is equal to nRT. We can write PV1 is equal to N1RT and PV2 is equal to N2RT. Then when we put these values of PV1 and PV2 in this equation, we get delta H is equal to delta U plus N2RT minus N1RT. Here delta H is equal to delta U plus, you know that N2 minus N1, that is delta N gaseous, RT is common here, RT. So for those reactions involving gaseous and reactant and gaseous product, delta H is equal to delta U plus delta N into RT. Delta N gaseous, reactant and products are in gaseous state. Now here you know that substitution of this equation, these values of or finally we get this equation delta H is equal to delta U plus delta N into RT. Now work done in a chemical reaction. Next point, work done in a chemical reaction. Work done in a chemical reaction. Work done in a chemical chemical reaction. Work done in a chemical reaction. Here, you know that work done in a chemical reaction is given by the equation W is equal to minus P external into delta V. You know that at constant temperature and constant pressure, the work done in the chemical reaction is given by the equation W is equal to minus P external into delta V. You know that if we consider that P external is equal to P, that means external pressure is equal to the pressure of gas, then W is equal to minus P into delta V. W is equal to minus P into delta V. That is equal to minus P into V2 minus V1. That is equal to minus P V2 plus P V1. So, work done in a chemical reaction is given by this equation. Now, here, if the gases are ideal, then from the ideal gas equation we can write, that is PV1 is equal, you know that ideal gas equation, PV is equal to nRT. Then we can write here, that is PV1 is equal to N1RT, and PV2 is equal to N2RT. Now when we substitute this value of P1 and P2 in this equation, we get W is equal to minus N2RT plus, that is N2RT plus N1RT, that is equal to minus N2 minus N1, that is equal to delta N. Here RT is common. That's why W is equal to minus delta N RT gaseous. So this is the equation for work done in a chemical reaction in which gaseous reactant and products are there in the chemical reaction. Then work done is calculated by using this formula. Okay, now if you know that, another example, for example, NH3 gaseous plus HCl gaseous, it gives, that is NH4Cl solid. Here number of moles of gaseous reactant, that is 1 mole of ammonia and 1 mole of HCl gives 0. Here there is no any gaseous product, means value of N2 is equal to 0 and value of N1 is equal to 1 plus 1, that is equal to 2. So W is equal to minus, in bracket, you know that 0 minus 2 into RT, that is equal to minus plus, that means here the value of work done is found to be, plus. Why? Because number of moles of gaseous reactants are more than number of moles of gaseous product. That's why work is done on the system by the surrounding. That means work done is found to be positive. Similarly, we will take another example, that is you know that hydrogen peroxide H2O2 liquid, 2 molecules, it gives 2 H2O gaseous plus O2 gaseous. Here number of moles of gaseous product are here 3. 2 moles of H2O and 1 mole of oxygen, and number of moles of gaseous reactant is equal to 0. That means here N1 is 0 and N2 is 3. Then from the equation you know that W is equal to minus delta N gaseous into RT. You know that minus that is delta N is equal to N2 minus N1, that is equal to 3 minus 0, that is equal to 3. So here 3 into RT, and you know that plus minus 3 into RT means work done is found to be negative. Work done is found to be negative. What this indicate? This indicate that work is done by the system on the surrounding. That means work done is negative. That is about the work done in chemical reaction. Then we will start the new point, enthalpy of sublimation fusion, that is phase transition, in next lecture.